thought you had a Macan.
No, if you scratch the Macan, that's somebody else's. If you've been out in the...
Is there
Bang on somebody's window this morning because they drove through the crosswalk while I was in it. Do not do that to me. I will dent your car.
with your car or with?
No, I was on foot.
Oh, nice.
I was walking through the crosswalk and somebody decided, well, I'll just go straight through this thing.
You're on campus?
On campus.
Oh, God. Well, everyone does.
I have no license plate and I haven't decided what to do about it. Banged on the window. I think I broke a toe once on a bus on 6th and Brazos because it saw me. I was crossing the street and it came up on the curb to make the corner. And I kicked that. I mean, I taught that bus a lesson. I kicked it so hard because I wanted to dent the bus. I think I broke a toe because my toe was sore for about a year.
Did it turn a different color?
No,
Oh.
no, it just hurt.
Oh. I flipped 3 toes last year.
You did?
Yeah. How? Well, I was playing a game and I was barefoot and I stepped my foot and someone said, so my toenails had a bit of color war. It was a new school. So there was dye on my foot, so the nails like got stayed purple. So just be cautious of that.
So we had a stab at trying to figure out what kind of reaction these unreactive aromatic materials might do. And it looked like they want to react with electrophiles because that would make sense, right? They're an area of high electron density. But if I do an electrophilic addition to them, then I lose a double bond. And by losing a double bond, I lose the big deal. I lose the aromaticity. So this is how they are all mostly going to react. Here's my electrophile. Now what's missing from this, because it's a nice ring structure, we never write those hydrogens in. We just plain don't write them in. So when you use the little stick diagrams, what happens sometimes is hydrogens pop up in the middle of the mechanism, and then when you don't need them again, they just kind of disappear. And that's going to be our case, but the first time through, we're going to write all the hydrogens out. All right, there are lots and lots and lots of electron density, very little electron density. Arrow comes from the place where there is electron density and it goes to the place where there is not. That means from the middle of the pi bond, not from any of these atoms, but from the pi bond itself. Okay. Goes out to the electrophile. This molecule, up to this point, has been symmetrical. So it doesn't matter. Markovnikov is not going to tell me anything at all about which one of these 2 carbons that I need to attach to. So take your pick. Those 2 pi bonds left intact. The electrophile adds to that carbon there at 2 o'clock, which leaves a positive charge on the other carbon. Now we're going to write these hydrogens in. And the thing to do, the only advice for doing this mechanism a little bit better that one way than the other, is to write this hydrogen in, that one, right there, closer to the positive charge than the new electrophile that you've just added. So this carbon now has 4 bonds. 2 to the ring, 1 to the new electrophile, and then 1 to this hydrogen. Write that hydrogen closer to the positive. Because the next thing that I'm going to do is take those electrons that are in that carbon-hydrogen bond and put them back into the ring. That gives me a product that is still aromatic. So, an aromatic material, area of high electron density. I have an electrophile, area of low electron density. I have a carbocation in the middle. Is that carbocation good, bad, middling, indifferent, or superior?
It's in the middle.
No. That's a really good carbocation. Why?
It's the worst one, right?
It's a single bond away from a double bond. I can move that. And when I move it, where is the positive going to go? From here to here. Double bond will move to there. And then the new positive charge that's here will be a single bond away from that double bond. So I can move it twice. That's a fabulous carbocation. Really, really stable. But this reaction would be a dud, completely non-starter, unless you get the aromaticity back. So the key to this is that step. Here, you reclaim the aromaticity. This is a really good carbocation.
So, I know we talked about aromatic structures and meaning their name came from the odor they produced. But when we're writing them like this, does it mean to have 3 double bonds?
Yeah. And we're going, once we get through this a little bit, we're going to nail down what being aromatic really means. And it means having a certain number of electrons in a certain arrangement. Now for us, right now, that is 6 pi electrons that are fully conjugated. That's double bond, single bond, double bond, single bond, double bond, single bond. I'm going to write down the rules. We'll get through it. You may as well do it now. It makes no difference. All right. What class of reaction is that? Remember, there are 3 big classes of reaction, and then there are subdivisions. So I've got eliminations, substitutions, and additions. Those are my big 3. Substitution. That's a substitution. I have replaced that hydrogen with an electrophile. So this is a substitution. What kind of substitution is it? It's an electrophilic substitution. It's not a nucleophilic substitution, because we don't have a nucleophile. We have an electrophilic substitution. So these now become electrophilic aromatic substitution. We shorten that to EAS, electrophilic aromatic substitution. All of our electrophilic aromatic substitutions share this mechanism. That is a template, and all of our reactions do it. Once or more. Sometimes you can do it more than once. Depends on what you put in. Okay, so there's a couple of things that we have to do. We have to show you multiple reactions that will build new and exciting substituents into the ring. We have to show you how to name them, and we have to define what aromaticity actually is, as Will have pointed out. Let's do that first. Remember we drew the little pictures for butadiene and said if those lobes line up, then it's double bond, and if those lobes line up, then it's double bond. And if you're clever and you make the two lobes in the middle line up, then you make a bond here as well. Okay. With a 6-membered ring, I have a double bond. So this is now planar, trigonal planar. It's flat. And it's a single bond away from another double bond. So that's flat. And then this is flat as well. So these molecules are going to be flat. And if they're not flat, then you basically, you break the big molecular orbital that's cycling the electrons around. So, we have a word. If the molecule is an annuline, which means it is cyclic, planar, and fully conjugated. Which means double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond. The double bonds are always separated by a single bond. So to be a cyclic, planar, fully conjugated molecule, you count as being an annuline. So if you write down a usual definition is, you have a cyclic, planar, fully conjugated annuline. It's redundant. Already have it. And then there's a trick. Because it has to be the right size. Not everything can be aromatic. And in fact, they take it in turns of being aromatic. Some material is non-aromatic, and then others is the absolute worst. They become anti-aromatic. All right. N is an integer. We all know what an integer is. It's a whole number. When n is 1, 4 times 1 plus 2 equals 6. And 6 pi electrons means 3 double bonds. So if your molecule is cyclic, 3 double bonds, and those double bonds are all a single bond away from each other, then you've met all the requirements you need in order to be aromatic, because that arrangement will automatically be flat and conjugated. Okay, when n equals 2, then 4 times 2 is 8, plus 2 is 10. And 10 pi electrons means 5 double bonds. This is something we're going to come back to after we're done with benzene, because that's where all of our interest really is. We're going to come back and look at some of the bigger molecules. Yeah.
What does N mean? Like, what's it for?
It's just part of the equation.
Yeah, but like, what makes it 1?
The fact that n is an integer.
Okay. So like, but what does the 1 refer to in the benzene?
It doesn't.
It's just like a variable.
It's the trend.
Okay.
It's 4 times some number plus 2. This is called Huckel's rule. Huckel actually has an umlaut over the U, so it's probably Huckel. But Huckel's rule says you have to have this number of electrons. And the meaning of n is nothing at all. It's just the trend line. It's just the way that the trend broke down. Three times 4, 4 times 3 is 12, plus 2 is 14. So that's 7 double bonds. So it looks like you have to have an odd number of double bonds in your molecule. An even number of double bonds, and we're not going to go down here. Even numbers of conjugated double bonds gives me something that is called anti-aromatic. And that's bad. That's the opposite. So you go to all this trouble of reducing the energy in your molecule by making it aromatic. And if you introduce another set of pi electrons, you destroy it. Okay, let's do some electrophilic aromatic substitutions. Make some new stuff, and then learn to name it as we go. Yeah.
I have 2 questions. So what does it mean to be conjugated?
Conjugation is when your pi system is a single bond away from another pi system. So I can put 2 pi systems in a molecule and have 3 possible scenarios. These pi systems are isolated.
Right.
Because they're too far apart from each other. They are more than 1 carbon-carbon single bond away from each other. I can have a double bond that abuts another double bond, so there's a carbon here, and then these are called cumulated. That turns out to be a bit too much pi electron density for that central carbon to hold on to. So these tend to be unstable. And then this conjugated one with a single bond between the 2 pi systems is the one where the electrons can flow from one place to another. Because if I'm only a single bond away, then I can push electrons from one place to another. And that delocalizing electrons is making your molecule have a moving target. And a moving target is more difficult to hit than a stationary target, and therefore introduces stability. What was your second question?
When you're figuring out the aromaticity with all those, do you just know that you're gonna divide whatever number you have in half to get your pi bond? Like how you have the.
Yes, so I can have a sigma bond, but that sigma bond is 2 electrons. Because a covalent bond, what's our definition of a covalent bond?
Sure.
2 electrons shared between 2 atoms. Okay, so every bond has 2 electrons. Now, if it's direct overlap, here's a P, and then there's another P. If I direct overlap those two, that's a sigma bond. It's still 2 electrons. Or I could have a pi bond, which comes from a P here, and then a P here, and they kind of merge in the middle. Still 2 electrons. So because I know that there are always 2 electrons per bond, or technically per molecular orbital, then I know that 6 electrons, 6 pi electrons means 3 double bonds. Okay? All right. Let's make some stuff. Every reaction is going to follow the same template. So all I'm going to do for every one of my reactions is change what's inside the box. Inside that little red box. It's my electrophile. So if I think of an electrophile, then I know that as long as I get the reaction conditions correct, I can throw it onto a benzene molecule and make a new substituted benzene. All right. That sounds easy. Only there's a snag. Electrophiles are positively charged. And that means that lots of the things that we want to add don't go. What if I wanted to make chlorobenzene? And I can make chlorobenzene. It's not particularly difficult. It means that I have to make that leap of knowledge because general chemistry has not prepared me for this. If I want to make chlorobenzene, what has to go inside this red box?
Something more negative.
No. You can't look what's on your page. I've erased it. What goes in the red box right here?
Something.
An electrophile. So this chlorine needs to be Cl+, which we told you in general chemistry is impossible. Only we lied. We didn't want your little brains to explode with too much information until you need it. Now you need it. All right. Chlorine, group 7, non-metal, therefore undergoes reduction quite easily, electron affinity, pulls an electron towards itself and goes negative. Chloride. This would be chloronium, which is absurd. Only I can make it happen. I can make that happen. What I need to do is I need to introduce chlorine to something that wants those electrons more than the chlorine atom here wants them. What is it that takes electrons away from other things? In the world of general chemistry words, this is a word that you know. Oxidation is giving up your electrons. Oxidation is the loss of electrons. Now, I'm going to break this chlorine-chlorine bond. We've seen it break, but we've seen it break that way. Actually, we've seen it break twice. That's homolysis. That's not what we're doing. What I'm going to do is I'm going to break this bond and take both of those electrons and give them to something else. And so the breaking of this bond will occur there, and this will go as join the new molecule as a chloride, and then this thing will be left behind as a Cl+. So, what action is being described on the board right now? 2 electrons being given to something else. What action is that? 2 electrons going from one place and joining something else. Something else goes here. We don't know what it is yet. All right, let's ask this question backwards. This thing, this unknown molecule right now, is going to strip 2 electrons out of that chlorine. What is it doing? What is it being? What behavior is that?
What's the step?
Basic,
What's the definition of a base?
accept,
Worst definition.
lose, or
Lewis is the best.
acids down, bases accept.
Okay. Yes. This is an acid. This is an electron pair acceptor. So what I need here is a Lewis acid catalyst. I need something that is starved of electrons. Where on the periodic table might I find an atom that no matter how hard it tries, just can't get enough electrons? Remember the octet rule from general chemistry? How many exceptions to the octet rule do you remember? 1. What is your exception? So what you remember was kind of the...
I actually remember there was one, but I don't remember which element it was.
Well, what was the rule? How did it...
Oh, hydrogen. Duh.
Okay, so hydrogen doesn't obey the octet rule because it only has a closed shell valency of 2. What other exceptions to the octet rule are there? Phosphorus can make more than 4 bonds. It can make 5 bonds. Like I say, phosphorus is supposed to have 3 bonds, right? Lone pair of electrons and 3. It can make 5. It can expand its octet. That's an exception to the octet rule. What else is there? What other exceptions are there? Use aluminum. What group is it in? Shouldn't have to look at the periodic table, people. What group is it in?
3.
How many valence electrons does it have? Okay. What is the chemical formula for aluminum chloride? How many valence electrons do each of those chlorines have? 8. And 8. And 8. How many valence electrons does the aluminum have? 6. 6. This is an electron deficient molecule. What can we do about that? Nothing. It's in group 3. It has 3 valence electrons. It's therefore limited to making 3 bonds. But if there's any AlCl3 floating around, and you bring a molecule of chlorine, Cl2, close to it, this is a Lewis acid. It's going to take those 2 electrons and say, yes, please. It's going to break the bond right there. Both of those electrons mean that this splits to be negative and leaves something else behind that's positive. So, what goes here is chlorine is my reagent. Aluminum chloride is my catalyst. It's my condition. We'd say that Cl2 plus AlCl3 makes AlCl4 minus plus Cl plus. So the mechanism for this is easy. The hard part is dreaming up how to make the bloody electrophile. Because that goes against everything that we were taught. But it is possible. You just have to know how to try. You just have to know how to try. Okay. So that is a Lewis acid catalyst. And we'll strip a chloride out of something else, therefore leaving a positive behind. Okay? Guess what I would do? If I wanted to make this. Exactly the same thing. Now you could opt to use aluminum bromide as the catalyst here, just to make yourself look nicer on paper. But there's no need for that. There's no need. AlCO3 will do. Same mechanism. All you have to do is discover the way to add the substituent by making the substituent an electrophile. Okay, this molecule is benzene with C6H6. This is C6H5Cl, and it's called, imaginatively, chlorobenzene. And this is called bromobenzene. At what numbered position is the chlorine attached to the ring? 1. Carbon number 1 now just became the position where the halogen is attached to the ring. Do we need to include the number in the name? No, because everybody reading it knows the rule. Same mechanism every single time. This time I'm going to make some nitrobenzene. All I have to do is figure out how I can get a source of NO2 plus. How is that going to be possible? So we think, what materials do I have available to me in the lab that contain nitrogen and oxygen? What did we learn in general chemistry, if anything at all, that contains nitrogen and oxygen? Nitric acid. What was the chemical formula for nitric acid? HNO3. And what do we know about nitric acid? It's a good acid, weak acid, strong acid. So what do strong acids do in solution? They dissociate into what? H plus. And oh, it's a negative, folks. That's too bad, because I was feeling kind of confident about that. What do we know about the behavior of that molecule, water? In the presence of acid, how does water behave? It's like a base. And in the presence of base, what does water behave like? Acid. It's like an acid. Which makes me wonder if that's true of everything. In fact, the water's right there in the middle. It reveals its hand. What if I took two acids and I mixed them together, and one of the acids was a better acid than the other? So I've got acid A, that is the universal sign for acid. Apparently, if you were in the 80s, you would know this. And then acid B, not as good an acid. Put those two together. what does the strong acid do? Still behaves like an acid. What is the lesser acid going to have to do? It's going to have to deal with the fact that the other acid is strong arming it, pumping all of its H plus into solution. It's going to have to act like a base. Has to. Got no choice. So what do I know that is a stronger acid than nitric acid? Who?
HCl.
If I mix these two together, I have a very strong acid and a strong acid. All right. Let the very strong acid be an acid. It's going to give away an H plus. Have the other acid behave like a base and pick that H plus up. What have you got? What does it make? It makes H2 NO3 plus. Doesn't look so good. But that molecule, H2NO3 plus, or that ion, has one nitrogen, lots of oxygen, and some hydrogens. And it doesn't look familiar to us, which might make us think that it's unstable. If it were unstable and were to perhaps dissociate into two smaller fragments, what do you think that one of those fragments might be? H2O. Okay, take that and strip H2O out of it. What are you left with? That gives you the NO2 plus that you clearly need here to make nitrobenzene. I need to add NO2. And because this reaction works when the fragments are electrophiles, that has to be NO2 plus. Elias Corey, who's a Harvard chemistry professor, won a Nobel Prize for doing what I just wrote on the board. Not this particular reaction, but there is a tendency for people to think, well, reactants turn into products, right? So if I figure out what my reactant is, I might be able to figure out what the product is. And in the history of the Nobel Prize in Chemistry, most of the prizes go to reactions that make something. Most recently, they're all going to medical, biochemical things. And occasionally, very, very rarely, somebody wins for a theory. And Elias Corey, 1990, that is so annoying, 1990 won the Nobel Prize for saying this: if you want to make nitrobenzene, you're going to need some benzene and some nitro. I kid you not. That is Nobel Prize. Apparently, before him, we couldn't have figured that out. Now, disconnect that. So on my reactant side, that means there must be something that looks like a ring, and there must be something that contains NO2, and I know that this reaction only works if that's an electrophile. I now know what I need. All I have to do is figure out how to make it. And I make it this way. That is now called retrosynthesis. It's also called a disconnection approach, where you figure out what you've made break it apart, which means that your reactants must be composed of those fragments. I find that particularly irritating because I was already in graduate school in 1990 and I could have figured that out for myself. All right, here's a big one. And it will dead end into the cliffhanger of what we will have to do the Wednesday that we come back after the MLK break. I'm going to add a methyl. Okay, so using Corey's method of disconnection and retrosynthesis. Retrosynthesis has its own arrow. A retrosynthesis arrow looks like this. And instead of pointing in the direction that it's pointing, what it actually means is go backwards. We're not going to, we may do it later in the year, but we're not going to do it now. Okay, which means I need a benzene, check, and I need a methyl, check, and that methyl has to have a positive on it. What did we learn from Organic Chemistry 1 about methyl carbocations? They don't exist. And yet I'm going to be able to do this reaction because I'm going to force it into existence. How am I going to do that? With another Lewis acid catalyst. Just make a new chloro. Save some money. That pair of electrons goes here as the chloride, and it makes Cl4 minus plus CH3 plus. So I'm going to CH3Cl and AlCl3. Now there's a little bit of refinement to do here, and we'll do it when we get back next week, of which particular Lewis acid catalyst to choose. I've gone for the big gun, the aluminum chloride, in all of the reactions that I've shown. Sometimes you don't want, if you can, you don't want to add the really strong thing to solution unless you need it. So there are times when we're going to use an iron chloride. There are times when we might use something that's boron. But this is guaranteed to do everything. All right, I'm done. What's the name of my product?
Methylbenzene.
Methylbenzene. Would make complete sense. Only that's not what we call it. Methylbenzene would, of course, be the systematic name, but it has a common or trivial name that is toluene. And toluene has made it into common usage because it is a very usable solvent. It is the smell of oil-based paint. It is the smell of oil-based adhesive glue. It's that, not particularly unpleasant, but it's that really strong chemical smell that you get from glue and paint. It's the stuff that people smell on purpose to get high. It's really, really stupid doing that because it turns off the motor part of your brain, the part that tells your body to breathe in and out.
So methylbenzene is tongue, but you don't call it methylbenzene.
We're going to go, I would love if we all called it methylbenzene, but we're going to call it toluene, which reveals some substituents change the name of the ring. Which means Wednesday we're going to be faced with a whole hour of naming.
Are we still not live on Tuesday?